Good morning, Excel Geo. And what we're going to do today is we are going to talk about prisms and cylinders. Now, yesterday we talked about polyhedrons. Now, when we look at today, we're going to look at a prism, which is a certain type of polyhedron. Now, we know a prism is a polyhedron because it is made of polygons, meaning every single one of the faces of my prism, it will be a polygon. A cylinder will not be a polyhedron, what we talked about yesterday, because a cylinder has two bases that are circles, and circles are not polygons. But we're still going to look at prisms and cylinders today. We're going to look at some similarities and some differences that the two have. All right. Now, we're going to start by looking at polygons and polygonal regions and how they are different. Now, we're familiar with polygons. A polygon is a plane figure with three or more segments as sides that intersect at endpoints. We've gone over that definition. How does that differ from when I say just a polygonal region? Now, that's the key thing. How does that differ? What am I talking about when I say a polygonal region? Well, a polygonal region is a polygon and its interior. So when I talk about a polygonal region, I'm talking about not only the polygon, the shape, but all the area inside of it. That's going to be represented by my polygonal region. All right. And that's how it would be different. Now, the next thing we're going to look at is we're going to compare when we talk about surface versus solid. What does that mean? Now, when I talk about a surface, I only care about the area of the faces, all right? Now, just the surface of the object. So when we talk about surface, you're only worried about the faces of your figure. And I want you to know, we can also, when I talk about surface, I can take a three-dimensional figure and I can cut it open and kind of lie it out as a net. So I can take my three-dimensional figure and I can make it a two-dimensional figure. So when we talk about the surface, we're talking about the faces, and it can be drawn as a two-dimensional figure. And that's when the net that kind of came up yesterday, when you can construct a net on a two-dimensional surface that folds to become a solid. All right, guys? That's what we kind of did yesterday. Now, a solid. Now, when I talk about a solid is the surface of an object and the knowledge about inside and outside that object. So this is where your surface is constructed to form a three-dimensional figure. So when you take that surface and you construct a three-dimensional figure, you have constructed a solid. And the solid is the entire thing, not just the outside, not just the surface, but the inside, the outside, the whole shape. All right? We are no longer the net. Okay? Now, how can we determine between the two when we're drawing? Now, if I looked at the surface of something, I can draw it as a net. So, like, for example, if I had a rectangular, if I looked at the surface and we said it could be a net, I could do a cube, which you did. I can draw it as one, I can draw a net, and that would be my surface. And if I folded that net, that would construct a solid. So if I folded my net, I would construct a solid, and that solid would be my cube. And you're going to notice that when I draw my solids, I put dashed lines to represent the segments that are behind faces. So you can see the three segments that are dashed represent they're in the back. They're in the back of my cube. And that's how I can differ between my surface of my figure and my solid. My surface can be folded to form the solid, but the surface can also just be a two-dimensional net. All right, guys? Okay. So let's talk about our first example. This is a prism we're looking at, and this is a box. It's saying a rectangular solid. So what is a box in geometry? When I say box, what do I mean? Now, a box is going to be a polyhedron with all faces in rectangular shape. So with all rectangular faces. That is what our box is going to be. And it's pretty much the same thing as a rectangular solid. Another name, boxes and rectangular solids are the same thing. It's a three-dimensional figure with 6 faces that are all rectangles. So when I say this, it's this, boxes are rectangular solid. You can use both words for the same object. So it is a three-dimensional figure. All right, guys, with 6 faces that are all rectangles. Now, this is actually also another name we might use is rectangular prism. Now, something is a prism if it has 2 congruent parallel bases. Now, in this case, it's hard to determine when you have a rectangular prism what the bases are because the bases can differ. Like I can say that these 2 are 2 congruent parallel bases. That would be one example. But the difference is in a rectangular prism, I can also state, in this case, I can state that the top and the bottom are 2 parallel congruent bases. So it's hard to determine what you want to identify as your base when we're talking about a rectangular prism. But when we have a pentagonal prism or a triangular prism, the pentagons and the triangles would be the bases, and all your other faces would still be rectangles. So there'd be the 2 parallel bases that are those different shapes would identify the name of that prism. So let's take a look at this. Parts of the box. Now your faces. What are our faces? In this case, our faces are going to be the polygons that make up the prism. In this case, since we have a box, a rectangular solid, it'll be 6 rectangular faces. So here we have 6 rectangle faces. Opposite faces. What will they be? They're going to be, in this case, opposite faces are the parallel faces. In this case, we have 3 pairs of opposite faces. All right, guys, 3 pairs of opposite faces, and they will be parallel and congruent. All right. So if I take a look at this, I could see in this case right here, if I was to identify a face, that would be a face. The top, it's pointing to the top of the box. That is a face of my box. Okay. And if you take a look, we obviously have 6 rectangles that form this rectangular solid, and we have 6 faces for this box. Now, edges, we're going to have, how many edges do we have in this figure? Edges are going to be every single segment that makes up this figure. So right here, this here is pointing to CH. CH is an edge. All right, guys. And edges, if I count up all my edges, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 edges in a rectangular solid. All right, guys. Now we can also say vertices. Here, vertices are where our segments intersect, okay? Our edges intersect. Right here, this is pointing to A. That is a vertex, one of my vertices. And if I look at this rectangular solid, I have 8 vertices. Now, this is an example of a rectangular solid. What makes a box or a rectangular solid a cube would just be that a cube would be a rectangular solid with all square faces. So a cube would be a rectangular solid with all square faces. All right, guys? Now, if we take a look at this diagram, we can name some parts. So this says name all opposite faces, and you guys can do that on your own. I'm just going to do one with you. Okay, opposite faces. An example of an opposite face would be the 2 that I have highlighted in purple here, ADFE. So I can say ADFE and BCHG. That's one pair. You guys can add the rest of them. There's more. Obviously, I said there's 3 pairs. You could also state that ADCB and EFHB HG are an opposite pair, and then ABGE and DCHF are an opposite pair. So they have all opposite faces there. Now it says name all the edges. Go ahead, name all the segments. I'm just going to go over a couple with you. You can fill in the rest. You have AE, AD, DF, and so on. Okay, guys, every single edge. Now we said there's 12 edges, so you can name 12 edges in this rectangular solid. Now, if we name all the vertices, this one's a lot simpler. We have 8 vertices. It's all our points. So it's A through, in this case, H. So it's just A, B, C, D, E, F, G, H. All right, guys. Now you can fill in all the other ones. I just want to make sure that you understand what our face, edge, and vertice are. Okay. When you're done with that, let's flip it over. Okay, that was a rectangular prism solid. Now we're looking at cylindrical solids, and we said these are non-polyhedrons because right here we have a base, and this is one of our bases, and this base is a circle. And a polyhedron has to have every face has to be a polygon. In this case, that's not the case. So this is an example of a cylinder. This is a cylindric solid, and it's a closed solid with 2 parallel congruent circle bases. It is not a polyhedron. So it's a closed solid with 2 parallel congruent bases. 2 parallel and congruent bases. All right, guys, that's our cylindric solid. And guys, you're going to notice it can be on a tilt. All right, we're also going to deal with prisms that can kind of be on a tilt. That is okay. All right, guys, and we're going to talk about that a little later on the bottom of this page. Now, if we talk about the parts, again, parts of a cylindric solid, bases will be 2 parallel congruent circles. 2 parallel congruent circles. Okay? Well, lateral surface. What do I mean by a lateral surface? Now, a cylinder has a lateral surface and a prism also has a lateral surfaces. That pretty much a lateral surface is all the faces excluding the bases. So it's all the face, all. So we're going to say all sides excluding the bases in this case. So this here, right here, see what that's pointing to? Everything. So everything around that cylinder. So if you were thinking of can, it would be that kind of around the can. You're thinking around the side. That is your lateral surface. So this is a lateral surface. All right, guys. Now, if I was to open the cylinder, if you would think about it and you were to open it, I would have a circle. I'd have like a rectangle in the middle as the base, and then I'd have another circle. This would be a base. This would be a base. And this here would be my lateral surface. If that helps you out, guys. That there would be my lateral surface. Now, the next thing we're going to talk about also is cylindric surfaces. So if I look at a cylindric surface, it's the 2 circle bases and the lateral surface. This would be everything. So in this case, it's the 2 circle bases and the lateral surface. That would be my cylindric surfaces. It would include everything, the 2 bases and the lateral surface. Now the height, the altitude is, again, the height of the cylinder. This is your height. Your height is the distance between the 2 bases. And what you have to watch out, guys, when I say that, it has to be perpendicular to the plane containing the base. If you're going from one base to the other, it has to be perpendicular to the plane containing the base. And that is actually true for both the cylinder and the prism. So if you look up here at this example, this here is my altitude. And if you look at that altitude, it is perpendicular right here. That altitude is perpendicular to the plane containing the base of the bottom. All right, guys, so let's talk about these cylinders and the prism. So here you go. Now here I have a cylinder. Now in this cylinder, I have two bases. And if I open this cylinder up, right here, I would have two base circles and that lateral surface. That lateral surface would actually be a rectangle. So my lateral surface would be one rectangle if I opened it up. Now that is my cylinder. Now here's an example of a prism. Now a prism, again, your prism is named based on its bases. Now your two parallel bases would be the triangles. This here would be a triangular prism. And that's based on my triangle. So my bases would be the two triangles. And my lateral area here would be different. It would be three rectangles. All right. I'd have three rectangles around the lateral surface of that prism. Okay. So when we talk about lateral surface, it's always going to be everything excluding the bases. So all the surface that does not include those two bases. All right, guys. The next thing we're going to look at is, again, down here, right versus oblique. Now, this right and oblique applies to prisms and it applies to cylinders. Now, you're going to have right prisms and right cylinders and oblique prisms and oblique cylinders. Now, what does that mean? Now, these here are two examples of triangular prisms because they both have triangular bases and that are parallel. All right, and they each have three rectangles as a lateral surface. So that is correct too. Now, what it makes one a regular prism, right versus oblique, a right prism, and one a oblique prism. If I look at a right prism, so that's what I'm going to look at first. Let's look at a right prism. If I look at a right prism, the right prism will have the angles between the bases and the sides are right angles. So that means if this is a right prism, the angles between the bases and the sides will all be right angles. All right. That is a right prism. Now you'll also notice that you easily can see the altitude of your right prism. Okay. The reason we can easily see that altitude of our right prism is because this here would be my altitude. My altitude would be one, if not all, of the edges that connect the two bases. That would be my altitude. All right, guys. So now let's take a look at our oblique. What makes this one different? What makes this an oblique prism? Well, it's going to be in the case, it is not going to have right angles. All right, so that here we have all right angles. The angles between the bases and the sides are not right angles. It's going to be tilted. It's almost going to look like that leaning tower of like Pisa, something slightly tilted. All right, where one base also doesn't fall directly on top of the other. Okay, now in this case, your altitude will not be one of your edges. So you have to be aware of that. All right, guys? Okay. So now let's take a look at the last definition that we're going to talk about. What makes something a regular prism? Now, before I go on to that, I want to actually go up a second real quick before I go on to that. I want to talk about I'm sorry, we're back here. I think there was an example up here. Yeah, here, cylinder. Now, this cylinder is a right cylinder. So just to use that word again, this here is a right cylinder. And what makes this cylinder a right cylinder? In a right cylinder, if I connect the two centers of the circle, that would be the equivalent to the altitude. All right, that would be the altitude. The circles would be directly on top of each other. That would be a right cylinder. All right, guys. Now, if I look up top more, this would be up here. I can call this an oblique cylinder. All right, that would be an oblique cylinder. All right, guys. And you can see the altitude there. It looks almost like a tilted building. Like you think of the Leaning Tower of Pisa, it almost looks like that. And the altitude, the distance between the two bases would fall outside of that cylinder. All right. It would not be I would not be able to find that altitude by connecting the center of both bases. All right, guys, just to make a note of that. Now, the last thing I want to go over is the definition of a regular prism. What makes a prism regular? Okay. And it's a little different here because, if you want to think about everything being exactly the same, the only you can have a cube. But when we talk about a regular prism, we are going to talk about a right prism with two regular polygons as bases. Meaning regular polygons, meaning all equivalent side and angles. Two regular polygons as bases. So the key word would be the two regular polygons. So you can have a regular hexagonal prism. If you had a regular hexagonal prism, it would be a right prism, where the two hexagons would be regular hexagons that are bases. All right, guys? So now in this example, if I look here, right here, I'm going to circle it real quick. This would not be a regular prism because the triangles are not equilateral triangles. Therefore, that is not a regular prism. All right, guys? You'd have to have two congruent polygons, which I don't, in this case, in that rectangle is a slightly different one. So two congruent polygons that are regular. So we don't have anything that we know is definitely a regular prism in these examples. Okay? But if we take a look, guys, down here, what I would like you guys to do is the practice right now. What you're going to do is take a look at this. Now, this one here, this is actually a good example. This would be considered if this is those pentagons, if those pentagons are regular pentagons right here, if these pentagons are regular pentagons, you would call this a regular pentagonal prism. All right, because it would be a right prism and it would have two regular pentagons as bases. All right, that would be an example. Now, what I would like you guys to do, your assignment for today, is to complete the next 2 pages of this packet here. So you have this practice. I want you to practice. I want you try to name the following. You name them after their bases. All right, guys. So that's how we name them. Then I would like you to do the drawing activity and try to do the hierarchy here. All right. And what we're going to do is I will make sure that I post the answers to all this tomorrow. Okay. Please upload your practice and all your answers to the hierarchy and everything to this assignment today so you can get credit for the day. If you have any questions, please visit me at office hours. I'm there to help you. Your quiz on 11.5, we actually extend 11.5 a little more from the textbook, will be not till next Thursday. So you have plenty of time to prepare. Otherwise, I hope to see you at office hours and you have a good day. All right, everybody. I'll talk to you soon. Bye.